Here we discuss the definition of a prime number and some properties regarding primality in the integers. So first let's start with the definition. An integer p is said to be prime if p is not equal to 0, it's not equal to plus or minus 1, and its only divisors are 1 in itself, plus, give or take a negative number. And so here's a couple of remarks before we move into some properties. P is prime if and only if negative p is prime. So if we're considering the factors of p, namely plus or minus 1, plus or minus p, and these are the factors of p. So then what are the factors of negative p? The factors of negative p are going to be what we get when we negate everything in here. So this is going to become this, which is precisely the definition of a prime number. Its only divisors are plus or minus 1 and plus or minus p. And so we see that if p is prime, negative p is prime. We also have this remark that if p and q are prime and p divides q, then p must equal plus or minus q. So if p divides q, then we know that q equals p times k for some k that's an integer. But q is prime, so by definition, its only factors are plus or minus 1 or itself. So if p divides q, then it must be a factor. But that means precisely that p must be plus or minus q. And k then has to be plus or minus 1. So now let's consider the following characterization of a prime number. It's a property that states if p is an integer that's not equal to 0, or plus or minus 1, then it's prime if whenever p divides the product of two numbers, it divides one of those numbers. And this is going to be an important characterization of primality. So let's prove this really quick. So we're going to let p be prime and let p divide its numbers the product bc. So let's say that p is prime and p divides b times c for some b and c that are integers. We want to show that either p divides b or p divides c. So let's let d be the greatest common divisor of p and b. Now, this implies that d has to be a positive divisor of p. So we'll write that first. And so what is this saying? If d is a positive divisor of the prime p, then the only possibilities we have are that p and b are relatively prime, or that p is actually a factor of b. And so if we write that, so we have that p and b are relatively prime, or p is a factor of b, which would imply that the d is plus or minus p. Okay, so, and we're just going to choose whichever one's positive. So let's suppose that p is a factor of b. So that means that if p is a factor of b, then it divides b because it's a factor. On the other hand, if p and b are relatively prime, since p divides bc, we have the precise setup of theorem 1.4 that we discussed earlier, which tells us that if we have two integers being relatively prime, and then we have that it's hard to say in generic terms, but basically if we have P, the greatest common divisor of P and B is 1, and P divides BC, then P has to divide C. And I encourage you to go back and look at that theorem to confirm that this is the precise statement that we need to make this conclusion. So what do we have? We have that in either case, P divides B or P divides C. And so we've shown that if P is a prime number and it divides the product of two integers, it has to divide one of them. Now, the important part to this theorem is the converse. It is also true. If P divides BC implies that P divides B or P divides C, then P is prime. So this is an important converse, and it's left to an exercise, but I just want you to think about it a little bit. It's quite important property, so make sure you pay attention to this particular homework in the assignment for this section. And then once again, note, this is true. Okay, so let's consider another property of prime numbers. So here in corollary 1.3.6, we had that if P divides the product of n numbers, then it has to divide at least one of them. And so let's prove this corollary. So let's, just assume what we're given. Let P be prime, such that P divides the product of n numbers, and we're calling those a sub 1, a sub 2, a sub 3, etc., all the way up to a sub n. Then note that we can write that the product of a1, a2, an is just equal to a1 times, the product of a2 up to an. Put an A3 there so you kind of see what's happening. And so by the previous theorem, we know that if P is prime and P divides a product of two numbers, then it divides one of them. And so what we're kind of thinking about, if we're thinking in terms of the last theorem, that this would be our B and this would be our C. And so we have that P divides B times C, and so it has to divide one of them. So by theorem 1.3.5 from before, we have that P divides A1 or P divides A2 times A3 all the way up to AN. So if P divides A1, then we found the A sub I that P divides. So we're done. If not, well then P must divide the other product. So P divides A2 times A3 times AN. But this is precisely, we can write this as, let's skip a line here to save space. Actually, let's just make an equal sign right here. This is the same thing as A2 times product of A3, A4, all the way up to AN. And so once again, we use this property from theorem 1.3.5. So again, here we go. So again, we have that P divides A sub 2, or P divides A sub 3, A sub 4, A sub n. So if P divides A sub 2, then we're done. And I've run out of room for done. So if p divides a sub 2, then we're done. Otherwise, it divides a sub 3, sub 4, a sub n. And so we can continue in this way. So we can continue. Hopefully by now you see the pattern. Namely, here in this next step, we would have either p divides a3 or p divides the product of a4 times a5, etc., up until an. So we can continue until we find sum a sub I, so that p divides a sub I. And note that we could have to take n steps. We could have to do this all the way until we get that p divides a sub n. But it's going to have to divide one of them because of this previous theorem 1.3.5. So note this will take at most n steps. So now let's look at the following example. If p is prime and p divides a to the nth power, is it true that p to the n divides a to the n? Well, let's see. So first note that a to the n is just a times itself n times. Okay, and so if p divides a to the n, which is equal to a times itself n times, what do we know? It has to divide one of the a. But we can just say, instead of one of the a, we can just say it must divide a. So let's make sure we're on the same page here. The last corollary said if p divided the product of n integers, then it must divide one of them. So here we have the product of n integers, namely the product of a with itself n times. So in particular, p would have to divide one of the elements of this product, but each element is precisely a, so p has to divide a. So then we can say, since p divides a, by the definition of division, a has to equal p times k for some integer k. Then we have the following. We have that a to the n is equal to, and we're going to substitute instead of a, we're going to write a pk here as our base now. And then if we multiply this out, we get p to the n times k to the n. And so what does this tell us? This tells us that p to the n, in particular, divides a to the n. So yes, it is true.